Okay. Now I'm going to try to share the screen. Okay, so what do I want to, oh, okay, so I can share that window and it won't be sharing my whole screen. Okay, so now what do you see? I don't hear David.
We see your PowerPoint window. It says Syntactic Formalisms. It's just the PowerPoint application.
Okay, and you don't see anything else. Okay, good. I think I finally got it. Okay, I apologize. Okay, so this is the lecture from last time that we were finishing up, and I'm going to scroll down to where we left off. So where we left off last time was that we talked about finite state grammars and context-free grammars, and we went over a thing called A to the N, B to the N, or center embedding, which we used to show that finite state grammars are not completely adequate for describing the syntax of human languages. And where we ended, we started to look at context-free grammars in more detail and to question whether they are adequate for describing the grammar of human languages. So we were looking at this slide, which has grammatical and ungrammatical sentences that are all generated by the context-free grammar on the left of the screen. The problem is that we don't want the ungrammatical sentences. We only want the grammatical sentences. Oh, this is not, okay. So, okay, so in order to write a context-free grammar that generates only the grammatical sentences, in the previous example that I was showing, we need to add more complicated categories. So you can see here that I've added a lexicon, which in addition to having determiner, noun, and verb, actually has complex categories: determiner singular count, determiner singular mass, determiner plural count. So for example, the word the can go with a singular count noun like book, or it can go with a singular mass noun like information, the information. The word this can go with a singular count, a singular noun like book or information. The word these can go with a plural noun. We have dog singular count and dogs plural count. We have information singular mass, but we don't have a plural of information. And we have two types of verbs, transitive and intransitive, so that we can say the information spreads, but we can't say the information spreads the dog. Because the rule says that, no, sorry, we can say the dog sleeps. Okay, I'm sorry, let me back up. I put spread in as, oh, I put it in as intransitive and transitive. Oh, that's interesting. So what you can't do with this grammar is say the dog sleeps the information. And that's because sleep is intransitive. And if you look over on the right, an intransitive verb phrase only contains a verb. It can't have a noun phrase like the information. So you can see how this more complex grammar can distinguish the ungrammatical from the grammatical sentences.
I don't think we can see the more complex grammar. We just see the one with the...
So the slide that I'm on now says context-free grammars are cumbersome.
Ours says limitations of context-free grammars.
So why would, when I advance the slides, why would it have not?
I think you're sharing the other screen. That usually happens. So we're looking at the PowerPoint application rather than your full screen presentation.
Okay. So, yeah, the other thing is that I have a tablet open. And I wonder if I have to advance the slides on the tablet. No, the slides advance on the tablet.
So, Sal, do you know how on a Windows machine to get this to work?
No,
What should she?
Sorry, I work on a Linux machine.
Hmm.
But usually you just select the other screen when you want to share. Is this is through Zoom, right?
Yeah, so let me try again.
When you share, you select which screen you want to share or which window.
Which window? So I think if you start the presentation.
Okay, wait, I'm going to share this one that says screen 2 because that's the tablet. Okay, what do you see now?
You see context-free grammars are cumbersome.
Yes.
Okay. Okay.
That's probably better.
Tablet and oh no, now I don't know how to write. And I just. Okay, I'm really sorry about my technical difficulties. Okay, so this is the grammar that I was talking about before that distinguishes transitive from intransitive verbs. So sleep is intransitive and it can be used in a rule that says, okay, can you see that I wrote something on the screen?
Yes.
Yay. Okay, so you can see that because sleep is intransitive, it's going to be used in a rule that says, my tablet just crashed down. Okay, it's going to be used in a rule that says VP intransitive singular goes to V singular. So let's get some class participation. What sentence can you make with that rule? VP intransitive singular goes to V singular. You can just speak up because I'm still having technical difficulties and I'm not even going to try to see the chat.
I'll monitor chat.
Okay. Can you say the dogs, which rules would you use for the dog's sleep? Someone tell me all the rules you would use, starting from the S, for the dog's sleep.
So in chat, we have S goes to NP plural, VP trans plural.
Is sleep transitive?
Sorry, intransitive. It's Arthur. I can't type,
Okay.
he says.
So you would start with S goes to NP plural, VP transitive plural.
VP
No.
intransitive plural.
Intransitive. Okay, I don't know how to erase that line. No, I'm writing all the wrong lines. Okay, the one with the arrow. I'm on a Wacom tablet, so if anyone knows how I erase that line, please tell me. It's the first time I've used it in class. Okay, and then what would we use for the noun phrase rule? After S goes to noun phrase plural, VP intransitive plural. What noun phrase rule will I use? Parentheses.
The third one.
The third one, noun phrase plural, which
Yes.
can consist of a determiner plural count. That's a determiner that can go with a count noun. And that would, then the word the can go with count or mass. It's in the dictionary twice. It's in the dictionary 4 times because the can be singular or plural or count or mass. And then a plural count noun, which is dogs. So, and then we would go on to the rule that has an arrow next to it. The verb phrase is the intransitive, no, sorry, it's plural dogs. The verb phrase.
So, by the way, according to the internet, you
Mhm.
can erase with your Wacom tablet by turning around the pen and erasing with the opposite side. But apparently that's not working.
No.
Oh, well, sorry to interrupt. I just.
Yeah, it looks like it has an eraser, but it's, I don't know.
Anyway, sorry to interrupt.
Sorry. Yeah, I'm sorry to have technical difficulties. Okay, so I would like to get class participation now to explain what the point of this slide is. I want to hear it in somebody's words other than mine. I mean, the slide says 2 things, one at the top and one at the bottom, but I want to hear in your words what you might not have realized before about context-free grammars.
So Arthur and Zach have answers.
Mm-hmm.
Arthur says, you need to be extremely specific and categorical in which words you allow in each category in order to guarantee the grammaticality of all words in a sentence. And Zach says, in order to get this grammar to work, you need a lot of different parts of speech.
Yeah, you need a lot of different parts of speech. Also, it can become, as we see, so thank you for those answers. Also, as you see at the bottom of the slide, if we added another type of verb or another type of noun, like another distinction in noun, like common and proper or something, we could end up doubling the size of the grammar. And the other thing is, just from an engineering perspective, if now we want to add ditransitive verbs, so a verb phrase consisting of a verb and 2 noun phrases, we would have to add it, how many places, let's see, we would need to add it in an S rule, and we would also need to add a VP rule. So every time we add something, we need to add it in more than one place. So from an engineering perspective, this is getting dangerous. And from a kind of computational perspective, it's also getting dangerous because it can become combinatorically large. Okay, so I'm going to talk about one of the earliest fixes to to context-free grammars that made them work better and be more manageable. And we're going to go into a little bit of a historical background now. But in the end, you're going to see how this led to the modern grammar formalisms that go beyond context-free. So what you're looking at now, I hope, you can see a finite state transition network at the top of the screen. And if I wanted to have this machine accept the sentence, the student saw the teacher, I could just go through this finite state network, determiner, consume the word the, then consume student for the word noun, as a noun, then consume saw as a verb, then consume the as a determiner, then consume noun teacher. So I could have a finite state machine accept that sentence, the student saw the teacher. So what's below that, though, is something else called a recursive transition network, which is also called a pushdown automaton, and which is equivalent to a context-free grammar. So you can see that each machine looks like a rule of a context-free grammar. So there are 4 machines labeled S, NP, VP, and PP. And the S rule has a noun phrase and a verb phrase. The noun phrase rule has a determiner and a noun. The verb phrase rule has a verb and noun phrase, and then a loop of as many prepositional phrases as you want. And the prepositional phrase has a preposition and a noun phrase. So first, let's look at how this works, and then we'll look at how Bill Woods extended it in 1970 to make it work more conveniently. So you can see a lot of small print here. I actually wrote out informally. This is not pseudocode. This is not code. I just wrote this informally about how you would parse a sentence like the student saw the teacher in the classroom. And I think what I'm going to try to do is write the stack on the tablet as we go through this. So you start in the S machine in the leftmost state. And so when I hover my tablet pen, I see a little red dot in the state that I'm hovering over. Do you see that?
We see it too.
Oh, goody. Okay. Okay, so I start in the leftmost state of the S machine, and the first arc has NP on it. And what that means is go to the NP machine. Get out of this S machine, go to the NP machine. But you need to remember where you left off. So when you're done with the NP machine, you know to go back to. So computer scientists will be familiar with this. And I'm going to write in a stack at the bottom here that we were in the S machine on the NP arc. So now we go into the NP machine and we consume a determiner, which is the, and then we consume a noun, which is student, and we get to the end of the NP machine. So now what we need to do that we've consumed two words and we're at the end of the NP machine. Now we have to go back where we left off. So we look in our stack or our memory, where do we leave off? We were on the NP arc of the S machine. So we cross that off. And we go to the end of the NP arc in the S machine. And now our instructions say, go to the VP machine. So we go to the VP machine, but we have to remember where we left off. We left off in the S machine on the VP arc. So we consume a verb, saw, and then the VP machine tells us go to the NP machine. So we're going to go to the NP machine, but we have to remember where we left off. We left off in the VP machine on the NP arc. We go to the NP machine and we consume the, and then we consume teacher, and now we're at the end of the NP machine. So we have to go back where we left off. We look at the last place, the most recent where we left off. That was the NP arc of the V machine. We cross that off. We go to the end of that arc. And now we have, we could stop there, but the problem is we can't stop because we still have words in the classroom. So we're going to take this PP loop. If this were an actual algorithm, I would be saying something different because we wouldn't know to take we would try different things until we found the right thing, but we're automatically trying the right thing here because I'm a person and not an algorithm. So I know I have to take this PP loop. So I go to the PP machine for prepositional phrase and I consume a preposition in. And then I find, oh, okay, wait a second. I didn't put that on the stack, that we were in the VP machine in the prepositional phrase arc. And then I consume in, and now I have to go to the NP machine, but I have to remember that I was in the PP machine on the NP arc. So now I go to the NP machine, I consume the in classroom, and now I'm at the end of the NP machine. So I have to remember where to go back to. Well, the last place I was the PP machine on the NP arc. So I go to the end of that arc. Well, now I'm at the end of the PP machine. So I have to remember where to go back to. So I go back to the PP arc of the VP machine. And now with some magic, because I'm human and not an algorithm, I know that I'm out of words. So I've just got to finish now because I'm out of words, consumed all the words. So now I look, well, where do I need to go back to finish the VP arc of the S machine? I cross that off. I end up at the end of the S machine. Yay, we finished. We consumed all the words. We crossed off all the items in the stack memory, and we're at the end. So this is called a push-down automaton. Does anyone have any question about it? Or want to say, wow, that was fun, or anything like that? Okay.
Wow, I like push-down automata. Not as much as finite state automata, but I still like them.
Yes.
I have a question.
Automata can be, you can parse in linear time on finite state automata. Push-down automata take usually n cubed or sometimes less. So they're polynomial. But you can see that you can write a very clear, easy to manage grammar. Whereas, so for example, we only have to write noun phrase is a determiner in a noun once in the recursive transition network or the push-down automaton. Whereas in the finite state transition network, we kind of had to write it twice, a little redundant.
So there are a couple of comments. One is from Abby Schrack, and she said, that was neat. I've heard the term, I guess, push-down automaton, but I've never actually seen what they are. And Tanmay Parekh says, I think I studied this in different contexts, but this is a great use case of such automata to know.
Okay, so this is basically a context-free grammar. That's really all it is. So now let's look at how this guy, Bill Woods, in 1970 made this better. So remember, we're trying not to have a complicated grammar like the one you see here. We're trying to make it simple. So how many bullets are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 rules here, and that would be 11 machines. But we don't really want 11 machines because there's something more systematic going on. So this is what Bill Woods did. He said, let's just have, oh, sorry, I didn't put the PP machine here. So if you add the prepositional phrase machine, that would be 4 machines. He said, let's add a lexicon and let's add something called a register structure. So a register structure is pairs of features and values. And you'll see that this became the basis of modern grammar formalisms, of basically all of the modern grammar formalisms. So root is a feature and student is a value. Number is a feature and singular is a value. Subject is a feature and its value is another register that has number, singular, and root student. So this is called a register structure. Any questions about that? In modern grammar formalisms, it's called a feature structure.
Is it just a key value store?
It's that the keys have to be, but there's number appears in more than one place. Does a key value store allow you to do that? So you have like the subject.
But you couldn't have more than one number per store, you know, but for each, if you have a separate key value store for each transition, right, then it would be like having just a list of named features, right? Of keys associated with values or features associated with values.
Is the question answered?
I think so.
Okay. So this is called an augmented transition network. And the red parts represent, unfortunately, separate code that you had to write. And I did try to supervise programmers to build these in the mid-1980s, and they didn't succeed because, oh no, some of them did have AI Lisp machines. But the memory filled up really fast because 16 megabytes of memory was a huge amount of memory at that time. And if you were really parsing as a real algorithm, you need to try a lot more things. So these weren't practical in the 1980s. Okay, so the red represents code. And so when you go into the, so let's start by what happens when you go into a noun phrase. So let's say you start in the first state of the noun phrase machine, determiner noun. When you read the determiner, you look up its number in the lexicon. And you find out that it says number singular. And then when you read the noun, and you record that in one of these registers, that we're looking, that this determiner has number singular. And then when you read the noun, student, you check its number, and a piece of code tells you that the noun and the determiner have to have the same number. So instead of 11 rules, we have 4 rules, 4 machines. If we had the prepositional phrase machine, that would be the 4th. But we have these register setting and register checking operations. And then when you go pop out of the noun phrase machine and you go back to the S machine, you put the information that you got from the subject. You got this out of the lexicon, that it's singular and that the root of the word is student. And you store that in the sentence's register structure. Now, the noun phrase network and the verb network are independent of each other. When you're in the verb network, you can't see what happened previously in the noun phrase network. But when you finish parsing the verb phrase with a verb like sees, you can then, you're back up here, you're back up in the S network, where what you've discovered about the noun phrase and what you've discovered about the verb phrase are now visible to each other. So that information about the noun phrase being singular that we discovered in the noun phrase network, and the information that we discovered about the verb being for a singular subject in the verb phrase network, that information has now percolated up to a place where the noun phrase and the verb phrase can see each other. And now they say, now here we are right next to each other. Let's check. Sees requires a singular subject. The subject is singular. We're good. So this is what Bill Woods invented, and it was called an augmented transition network. So I'd like to hear in somebody's words, maybe somebody other than Arthur or Zach, what was important about what Bill Woods invented in 1970. So while you're writing, I'll just say again that this became the basis of all the modern grammar formalisms. David, is anybody writing?
Nobody is writing.
Oh dear. I'd like to hear it in your words. Oh, and I said not Arthur or Zach. You need to hear it in somebody else's words. If you don't say it now, I might make you say it on a quiz. So nobody wants to say anything. Let me ask some questions. Does it seem worth the trade-off to, okay, so what about on this slide, what it says about trade-off? If you keep the formalism simple, that is, you just keep it to a context-free grammar, you get a proliferation of rules and categories that's hard to manage. But if you make the formalism more complicated, now we have a context-free grammar plus a set of operations for setting and checking values in registers. Now the grammar is in some ways more simple. We took the complicated part and we loaded that off to another part of the formalism. What do you think of the trade-off? Anybody have an opinion? Okay, then I'm going to go on to the next set of slides. Click to exit. Okay, so let's hope that I do this right.
Danny said, can you repeat the task? And Arthur said, it's training versus runtime processing, basically. And Jenny said, I think if we have a simple formalism, then it's easier to generalize to other languages. And Sadesh says, I feel like adding more to the formalism is better.
Wow, so we have conflicting opinions. So was it Janny who said that the simpler formalism generalizes to different languages better?
I wasn't very sure when I was writing that. What I was thinking was that maybe, especially if we are looking at it from like maybe linguistics point of view, then if we have a single formalism, then then like we can probably reuse the same sort of computation or algorithms that we need if the formalism is kind of like consistent, because otherwise we may need to like add more to the formalism when we get more data, but I may be wrong. I may be misunderstanding the question a little.
Okay, the way I described the augmented transition network, where I talked about the writing in red being code, at the time of augmented transition networks, that code was specific to English. And that code would have to be rewritten for another language.
Oh, all right, thank you.
Okay, but in the, what you'll see on Wednesday, that in the more common, in the more modern grammar formalisms, the extra additions to the formalism are designed to do everything that any language needs to do. So it's a more elegant type of thing.
Oh, all right.
What other comments? So I'm not screen sharing, so I can look at the chat now. So Tan May said, can we do something in the middle? Simple formalism to handle major cases, exceptions handled separately with another network. Okay, this is all, and Salvador says, linguists are in industry are paid to find that balance. Yeah, and sometimes they make funny decisions like, oh, let's just do context free. You can parse it in linear time. That makes other things hard. Let's see, Arthur said training would be building the grammar, generating the rules, and runtime would be applying it. Yeah, that could. That's interesting.
I think that this is going back to Arthur's comment, it's training versus runtime processing, basically. Mm-hmm. And then Salvador says, is there training time here at all? And so Arthur is responding to that.
Yeah, there's rule writing time. Now the question is, can you write the rules one way and then compile them into a context-free grammar? Context-free grammar, we know, can be parsed in less than n³ time. So for linguistics majors who are not studying computer science, I don't want to leave you out of the discussion, but that just means that if the sentence has n words, the worst case of how many steps the algorithm will go through is n cubed, where n is the number of words. So if you look on this slide where I went through, where I had a bullet for each step that we went through in parsing the sentence, the student saw the teacher in the classroom. Each one of those bullets is kind of like a step in the algorithm. Not exactly, but more or less. And because I'm human, I didn't do all the steps that an algorithm would have to do, because I already know how it turned out. So you can go up to needing n cubed steps to parse a sentence. But with augmented transition networks, now you're getting into full computing power. You can go way harder than n cubed, slower, more time, more steps. So that's bad. So I think what Arthur was saying was, could you write the grammar in a notation that's convenient for humans to write it in, but then before you run the grammar as a parser, turn it back into something that can be parsed in less than n cubed time. Yeah, it may be possible, but that's not what people do. Okay, let's go on, and we're going to leave that question open, the question of the trade-offs between a simple formalism and a more complicated formalism. Oh, and Salvador says, why not let a neural network find the right balance and write the rules for you? They kind of do. Well, they don't change the formalism, but yeah, you can give tree banks to a neural network. They don't find the formalism. You give it the tree bank and it parses. You still have to design what you want the trees to look like. But yes, you can make the neural network parse, and then it will not have interpretable states like the push-down automaton. It'll have attention heads that kind of know about verbs and objects, and attention heads that kind of know about possessors and nouns, but it'll be kind of dreamy, and the rules won't be in there explicitly.
And you won't be able to tell why it doesn't work. As far as I can tell, there are like two stages of neural engineering. You know, like one is my model doesn't work and I don't know why. And the second is my model works and I don't know why. You know.
But the other thing that I haven't pointed out yet is the difference between a robust parser and a precision parser. So when you are parsing queries that people write in Google, like how old is Kamala Harris? You want a robust parser. So if somebody said, how old are Kamala Harris? You still want to parse it. But if you're writing a precision parser, you might be writing a precision parser for Duolingo. It should tell students if they've made a mistake, or maybe for Grammarly, or maybe those lines that Microsoft Word puts under things that aren't, where the grammar's not quite right. Or maybe you're generating language and you want to generate only correct sentences. And so in those situations, you need a precision parser. So neural parsers are usually robust parsers. They'll give you a parse of anything you give them. If it's not grammatical, they'll come up with the closest they can get to what maybe would be a structure of a grammatical sentence. But a precision parser is necessary in some cases, and that's different from a robust parser. Any questions about precision parsing and robust parsing? Okay, I'm going to try to share the screen again. But I'm either knocked my tablet out. It doesn't see the tablet anymore. But my screen is duplicated on the tablet. Hang on, I'm going to take another What?
Zoom doesn't see your tablet anymore, or
No, when I'm looking at the
um,
things I can share, before it said screen 2, and now it doesn't say screen 2. And actually, when I exited from the last set of slides, it said screen sharing stopped because second display was lost. So,
oh, can you try putting PowerPoint in presentation mode and then try sharing again?
okay. Um, okay, put PowerPoint in presentation mode.
And then switch to Zoom and share screen.
Okay, so I've got PowerPoint in presentation mode. Oh no, but now I can't get to Zoom because PowerPoint's in, oh wait, I can minimize this window. I want to minimize it more. I can't see where, okay, so now I can go to Zoom. And now I can go to share screen. And now I see screen 2. Great. Okay, thank you. Again, I apologize for the technical difficulties because this is the first time I've used this tablet. Okay, so on Wednesday, we're going to go back to how the modern grammar formalisms built off of the augmented transition network. But before we talk about that, we have to talk about some background about grammar, which is constituents and dependencies. Okay. So on this slide, we see 2 representations of something called constituent structure and 3 representations of something called dependency structure. So let's start with the constituent structure. At the bottom right, you see the batter hit the ball. And you can see that the batter is grouped as a constituent, and hit the ball is grouped as a verb phrase constituent, and the ball is grouped as a constituent. And you can see something notationally equivalent in parentheses at the top right. What you see at the top right is the notation that's used in the Penn tree bank. So the first open parentheses is the sentence, and then you have the noun phrase in parentheses, and then you have the verb phrase in parentheses. The dependency parses represent the sentence in a different way. So if you look at the top left, you see that the main word of the sentence is hit. And it has 2 dependents, batter and ball. And the edges that connect hit to batter and hit to ball have labels on them. So this is called a labeled dependency. So hit is connected to batter with a subject label, and hit is connected to ball with an object label. And batter is connected to the, I just used modifier label here. In universal dependency tree bank, it might be something different. And ball is connected to the with the modifier label. In the other 2 representations are equivalent. The one that says subject 2-3 mod 1-2, what that means is word 2, batter, is connected to word 3, hit, with a subject label. Word 1, the, is connected to word 2, batter, with a modifier label. Word 5, object, is connected to word 3, hit, with an object label, and so on. And you can see that reflected in at the bottom of the screen without numbers. So any questions about these 2 types of representation, dependency structure and constituent structure? We're going to look at them in detail. Okay, so I want to remind you one of the reasons why grammar exists. we want to communicate meaning, but why would we have grammar? Why does grammar matter? And this came up for the LTI students. This came up in Friday's colloquium. And I'm giving a pretty similar answer to the answer that Ev Fedorenko gave on Friday. The words need to group together into meaningful units. So last time we looked at the old man is yawning versus the old man the boats. So in the first sentence, the old man is a unit of meaning, meaning an elderly person. And in the second one, the old man the boats, man is a verb, meaning to staff or work on. And the old man is not a unit of meaning in that sentence. So one of the uses of syntax is to group words into units that are useful for interpreting the sentence. And what we saw before was the two approaches to syntactic structure. In dependency grammar, the basic unit of syntactic structure is a binary relation between words called a dependency. So for example, the relation between batter and hit. Batter is the dependent, hit is the head, and they're in a dependency relation that is labeled subject. In a constituent structure, the most important construct is the constituent, which is a complete subtree, like a noun phrase or a verb phrase. So we have one approach where the basic unit of analysis is a dependency, a binary relation between words, or a relation between two words. I guess that makes it binary. And in a constituent structure, the most important unit is a constituent, a complete subtree. Okay, any questions before we go on?
Are these graphs always directed, or they are undirected?
They're directed. Oh, they're directed, but this one is a tree. So each word is dependent on exactly one other word.
Okay, thank you.
But in extended dependencies, words can be dependent on more than one other word. So this is a tree and the edges are directed.
And in that case, could it become cycled, or it has always to be uncycled?
It sort of depends on who you ask, right?
Yeah, I've heard.
Like you can have cyclic, you can have cyclic graphs, dependency trees that are cyclic graphs. But in some versions of dependency grammar, like universal dependencies, that's not okay. All of the, everything is a DAG. It's a directed acyclic graph.
Yeah, and right, and in lexical functional grammar, it's also always a directed acyclic graph.
Thank you.
Okay, so last time, or the time before that, we talked about reproducibility in linguistics, having diagnostics or tests, so that if two people are analyzing the same word or the same sentence, they can come up with the same analysis. So we talked about tests with respect to parts of speech. So if I take a word like which, W-H-I-C-H, and I ask two different linguists, is this a determiner or not? In order to get agreement, the two linguists would apply the same set of diagnostics. And just to review, one of the diagnostics we used is that it makes a singular count noun grammatical. So you can't say book is long, but you can say the book is long, and you can say which book is long. You can't say book is long because a singular count noun can't occur by itself without a determiner. So by that diagnostic, which would be a determiner. So now I want to talk about coding manuals, just as an example. Because, so linguists label data with parts of speech and with constituents and with dependencies. And then machine learning algorithms learn to assign parts of speech or learn to analyze the structure of sentences based on the examples that the humans wrote. The humans traditionally have had very big coding manuals, manuals of diagnostics that you can use. So for the pen tree banks, the part of speech coding manual is 30 pages of diagnostics. And for the pen tree bank, the coding manual for constituents is more like 300 pages of diagnostics. And I have seen longer manuals than that. So we're going to go over a little bit of what these diagnostics look like. So first, the definition of constituent. You can define it as a string of words, or you could define it as a subtree. If you define it as a string of words, it's a string of words such that there is one node that dominates those words and no others. If you define it as a subtree, it's a complete subtree consisting of one non-terminal symbol. And if you just grabbed that non-terminal symbol and yanked it out of the tree and everything under it came along with it, that would be the constituent. So we've already gone over phrasal categories, that we have lexical categories, parts of speech, determiner, noun, verb, adjective, preposition, and we have phrasal categories like noun phrase and verb phrase. Let's review. Linguists use somewhat different terminology than you might have seen in computer science. We talk about the node above a node as its mother, and the node below as its daughter. So we would say that noun phrase, let's see. So this is a, can you see my, no, my tablet's not writing anymore. Hang on, I'm trying to get the tablet to write. Okay. So mother, daughters, I'll just write D for daughter. And then these two are sisters. I'll just write S. Ooh, that wasn't right. And other terminology, a node that's above another node dominates it. If it's right above it, it immediately dominates it. And we've also talked about phrasal nodes and lexical nodes. So that's just some terminology. Let's look at some trees. Sam climbed up the ladder and Sam picked up the ladder. So let's remember the definition of constituent. A constituent is either a complete subtree or it's a string of words like up the ladder, such that, let's just take the ladder. The ladder is a complete subtree. So if I grab this noun phrase node and I just yank it out of the tree with everything under it, I'm going to get the determiner node and the noun node and the and ladder, and that's a constituent. Or I could look at a constituent in terms of saying that the string of two words, the ladder, is a constituent because there exists a node, namely noun phrase, that dominates the and ladder and nothing else, only the and ladder. So that's the definition of constituent. So now looking at these two trees, what can you find something that's a constituent in one of the trees, but not the other tree? So now I'm waiting for answers.
Could you please repeat the question?
Something that's a constituent in tree 1, but not tree 2, or something that's a constituent in tree 2, but not tree 1. Any answers yet? So let's say a string of 2 or 3 words that forms a complete subtree in tree 1.
Can you see the
Oh,
chat?
no, I can't see the
So
chat.
so Sinesh said, sorry, can you go back a few slides to the definitions? But Zach says picked up versus climbed up, and Abby says picked up is a constituent in 2, but not in 1. Arthur says up the ladder versus just the ladder also works, I think. And Sophia Ho says up the ladder is a constituent in 1, but not 2.
Okay, I think those are correct answers. In tree 1, up the ladder is a constituent. In tree 2, up the ladder is not a constituent. The reason it's not a constituent is that there is a node that dominates the words up, the, and ladder, namely VP. VP does dominate those words, but it doesn't dominate only those words. It also dominates the word picked. So up the ladder is not a constituent in tree 2. Picked up the ladder is a constituent, and picked up is a constituent in tree 2. Okay, is that, any questions about that? Okay. So now we're going to talk about tests for constituency. And we are going to need to go into a background about transformational grammar. Because although we will not be using transformational grammar, the metaphors of transformational grammar have influenced the terminology that we use. And so we use movement as a metaphor, and I want to explain why we do that. So we talked about this previously, so I'll just say quickly, a transformational grammar consists of a context-free base that generates basic sentences like the students ate chocolate and a dog bit the man. But it does not handle all sentences. Other sentences that have the same semantic roles, like chocolate was eaten by the students, or the man was bitten by the dog, where again, the man is the patient and the dog is the agent. That's the same as a dog bit the man. A dog is the agent and the man is the patient. So transformations, which are also called meaning preserving tree-to-tree mappings. So they map a tree to another tree and they preserve meaning. The part of meaning they preserve is the semantic roles. So you get some sentences from a context-free grammar, and you get the rest from transformations that move things in tree-to-tree mappings. Okay, so that's why we talk about things moving. So for example, if we start with Sam climbed up a ladder, there is a movement construction called topicalization that allows you to move something to the beginning of a sentence in English. So we can have up a ladder, Sam climbed. And so I've put, using the metaphors of transformational grammar, the deep structure is Sam climbed up a ladder. And in the deep structure, up a ladder is after the verb climbed. So here I've put in gray where up a ladder was in the deep structure. But then a meaning preserving tree-to-tree mapping that doesn't change the semantic roles moves up a ladder to the beginning of the sentence. And then we call that its surface position. So we would call this its deep position. And we'll call this I can't get used to the fact that I'm allowed to rest my hand on this tablet. My son is trying to train me on that I can actually write neatly because it doesn't respond to my hand. So it only responds to the pen. Okay, another transformation is called clefting. Cleft means to cleave or cut something. So you cut the sentence. I decided to cut it this time between likes and chocolate. And then you take the piece you cut off. I like the idea of cutting off pieces of chocolate. And you add the words it is and the word that. So that's the transformation. Chop off a piece of the sentence, put the words it and is, then put the piece of the sentence that you chopped off, then put the word that, and then put the rest of the sentence. So you get, it is chocolate that Sam likes. So again, this is the deep position, but you don't pronounce the deep position. Is that pretty clear? The gray part, you don't pronounce the gray part. You pronounce the surface position. Any questions about that? So although we no longer think of these as movement rules, we no longer think of things as moving around the tree, we still use the metaphors of transformational grammar to call these movement rules. So is that pretty clear what I mean by these movement rules, topicalization and clefting? Any questions? Okay. So let's look at how to perform a test for constituency. So suppose we want to know whether up a ladder is a constituent. And we don't know. We don't know because we're confused for some reason. Climb up a ladder, pick up a ladder, and we're just not sure what's going on. So we start with something that we're really sure of. We're really sure that into the room is a constituent. So just to validate our diagnostic, we start with something we're really sure of. So we're going to do a cleft here. I'm going to chop off into the room. And then I'm going to add the word it and the word was, and then the piece that I chopped off, and then the word that, and then the rest, he ran, the remainder of the sentence. And I get, it was into the room that he ran. So now I've verified, okay, into the room, I'm sure is a constituent, and I can move it in a cleft construction. So that I've now validated my test on something that I'm sure is a constituent. So now I'm going to take something that I'm not sure about. I want to say, what about he climbed up a ladder? I want to know whether up a ladder is a constituent, like in the room. So I'm going to chop it off because I'm going to apply the clefting test. And I'm going to use the word it and the word was. And then the piece that I chopped off. And then the word that. And then the rest of the sentence, he climbed. And I get, it was up a ladder that he climbed. And that sentence is grammatical. So we're going to say that up a ladder passed the test for constituency. Now, let's look at, he picked up a ladder. So again, I want to know whether up a ladder is a constituent. So I chop it off, and then I use the word it and the word was, and then I take the piece that I chopped off, up a ladder, and then I add the word that, and then the rest of the sentence, he picked. It was up a ladder that he picked. So how does that sound? I need responses.
So Arthur says, the last sentence is grammatical for me though it doesn't mean the same thing as the
Ah.
previous sentence. For example, it was up a ladder that he picked the apples. Not good for me,
Oh,
but
no, that's a different one. Suppose he picked this ladder and not that ladder. It's a ladder, this is a ladder that he picked. So, okay, but we needed, but remember, these were meaning preserving tree-to-tree mappings. So we're going to try to get an interpretation of the sentence that has the same semantic roles as the original sentence. So when you judge whether it's grammatical or not, you're going to judge whether you can say it meaning he raised something up against the opposite direction from gravity, and that thing was a ladder. We're going to preserve the original semantic roles. And can this sentence, it was up a ladder that he picked, mean the same thing as he picked up a ladder? And Arthur is correct in pointing out, no, it can't mean the same thing. It might be grammatical, but it can't mean the same thing. So whatever transformation we did, it wasn't meaning preserving. So if the transformation results in something that's ungrammatical or something with a different meaning, that means the test failed.
so Arthur says, wait, so we are not treating this test as strictly one of grammaticality? That's how I've been taught it in the past.
No, well, when you've been taught it in the past, they just didn't tell you the second part. They knew that. Because I'm sure that if you were in a linguistics class applying tests for constituency, that the situation must have come up that the sentence is grammatical but doesn't mean the right thing. I'm sure that situation would have come up, and whoever taught that class would have said, yeah, it's grammatical, but it doesn't mean the same thing. So I'm just making...
Yeah, he says it was a very theoretical syntax course. We were not allowed to use meaning as an argument.
Ooh, no, but okay, Arthur, I'll talk to you about it later. Meaning is central. Was it Chomskyan minimalism? Semantic roles are driving Chomskyan syntax, absolutely driving the syntax. So I'm sure that I'm not disagreeing with your other teacher. It's just, we might have stated the definition, and because I know your other teachers. If they were at CMU, it was Mandy, Tom, or B, and I know all of them, and I know that I'm not disagreeing with them. I'm just sort of making something explicit that they didn't.
Arthur says, I don't think you are.
Yeah, okay, good. I'm not disagreeing with them. But I'm saying that to pass the test, the semantic roles have to stay the same. The meaning has to stay the same, and it has to be grammatical. Okay, so let's look at what we found. We found that when we apply the constituency test to up a ladder, and we say it was up a ladder that he climbed, that's grammatical, and it means the same thing as he climbed up a ladder. Now, we saw a couple lectures ago, it's an answer to a different question. It's an answer to the question, what did he, or where did he climb? And then the answer is it was up a ladder that he climbed. Versus who climbed up a ladder? It was him who climbed up a ladder. So it's an answer to a different question, but the semantic roles are the same. But when we try to do the constituency test on he picked up a ladder, it comes out ungrammatical or not meaning the same thing. And that is why we wrote the trees this way. We wrote this tree number 1 for Sam climbed up a ladder because up a ladder passes test for constituency. And we wrote this tree a different way because up a ladder does not pass test for constituency in this sentence. So I need to hear, we just have a couple minutes left, but I need to hear from the people who have not previously worked with tests for constituency, and to see whether this makes sense. That it's the words up a ladder in sentence 1 that caused us to build tree 1. Because in sentence 1, up a ladder passes a test for constituency. And therefore, when we build a tree for Sam climbed up a ladder, we build a tree in which up the ladder is a constituent. But when we build a tree for sentence 2, we build a tree in which up the ladder is not a constituent.
So Sadesh says, I think it makes sense.
Okay.
Although it was up a ladder that he climbed seems to have two meanings for me.
Yes, what's the other meaning? Oh, yes, a ladder, it was like, where
It
is
was a
the,
climbed ladder.
yeah, it was a climbed ladder. Where is that bird's nest? Oh, it was up that ladder that he climbed. Yeah, that's a different meaning. So it's allowed to have an additional meaning as long as it has the original meaning. Sounds like,
Tenmei,
what?
sorry.
Go
Tenmei
ahead.
says, I understand the difference in the trees and why does it exist, but I don't know, do we automatically build such trees? I think there's some typo there, but I think but I don't know how we automatically build such trees.
You mean how a person builds the trees or how a computer would parse the sentence?
A computer, I meant, he says.
Yeah, if a computer was parsing the sentence, it would either be neural or it would be probabilistic grammar. And it would know, if it's neural, it would know about the surrounding words. And it would have been, yeah.
If it's like a PCFG, for example, going old school, then it doesn't know about the tests for constituency, but it's learned the patterns from the person who created the tree bank. So they used the test for constituency, and then it learned these patterns probabilistically, and then can reiterate the same like patterns of parsing, right? But with a neural parser, then well, sort of the same thing is true, right?
Yeah.
Is that correct?
That's what I was thinking, that humans use the test for constituency. Humans build the trees, and then either in the old days of probabilistic context-free grammar, or these days a neural network, learns from the trees that the humans built. And the human knowledge of constituents is latent in some states somewhere.
Tenmei says, okay, got it. That makes sense.
Mm-hmm. Okay, I want to say one more thing, but David, were you going to say something else about constituency? I want to talk about quizzes and homework. Okay, a quiz will be posted today on morphosyntax. So there were 5 lectures on morphosyntax. You should review them. And the quiz that will be posted later in the early evening, and we will be due on Friday, is about morphosyntax. And then there will be a homework assignment on morphosyntax that I will post either late this evening or tomorrow. And it's going to involve, I'm going to give you languages. I'm going to give you, you're going to write interlinear glosses. You're going to add morpheme glosses to sentences. And you're going to have to figure out which labels to put on the morphemes. So that homework will be posted later today or tomorrow. Okay, anything else for today?
Sounds good.
Oh, okay. I'm still trying to operate my technology. Okay, I'm out of the screen sharing. No. Okay, well, I tried to figure out which mouse controls which machine. You guys can
Bye-bye.
see you on Wednesday.